Okay, hi everybody. This is going to be objective I2. So I gave you a lot of do now questions at the beginning of the video that are pretty important, and I just want to go over them. Just remember the questions that you answer in these Edpuzzle videos are just graded for completion. Don't worry if you get it wrong. I'm mostly just trying to get you to think, and get the brain working and thinking in the right way. And I just kind of like to see what you think, when I look at your answers. But as long as you answer everything and watch all the videos, you'll get full credit. All right, so number one was a review of the last objective. So photosynthesis, it converts the energy that we get from the sun, which is radiant energy. Remember, any electromagnetic wave is radiant energy, whether it's visible light, whether it's ultraviolet, radio wave, gamma wave, X-ray, infrared, all of those. They all have radiant kinetic energy. So you could add the word kinetic if you wanted to. And what the process of photosynthesis does is it takes that energy and converts it and basically, makes its own, the plant makes its own food. It basically takes that energy, converts that into making molecules that have really energy rich bonds in them. So it converts radiant energy into chemical energy. And as we know, chemical energy is a type of potential energy. So it's not really doing anything. The glucose and the sugars that are produced in photosynthesis are just kind of sitting there, but they're kind of a stored up energy source that the plant can use later on, or that an animal can use that eats the plant or whatever. All right, these next questions are kind of a preview of what we're getting into in this objective, okay? In this objective, we're gonna be talking about heat. And a lot of people think that heat and temperature are kind of the same thing. They are related, but they're not the same thing. It is true that if something is hot, it does have a lot of heat, but there are other things that determine the heat in something besides just how hot it is or how cold it is. Heat's kind of a broader conceptual thing than temperature is. Okay, and each of these questions kind of gets at one of those things, those factors that determine how much heat is in something. All right, so imagine you put a 10-gram sample of iron and a 30-gram sample of iron in a 200-degree oven, okay? Which sample will reach 200 degrees first? Okay, so as you know, these are at room temperature, I'm assuming, when you put them in the oven. And then they're going to heat up and they're going to heat up. And once they reach 200 degrees, they'll stop heating up because it's reached what we call thermal equilibrium. Once the sample of irons and the air in the oven are the same temperature, the temperature will stop going up. The one that's going to reach 200 degrees first, you probably guessed correctly, is the 10-gram piece. Just because it's smaller, it's going to be able to get there first because it basically needs to absorb less heat from the surroundings to get to that temperature. Whereas because this has more particles in it, it's going to need longer to absorb more heat from the surroundings. It will get there eventually, it just won't get there as fast as this one. Once both samples have reached 200 degrees, which one will have more total heat? Okay, this is the kicker, okay? A lot of people assume, well, that one heated up faster, that must have more heat, we assume that things that heat up really quickly, they must have a lot of heat. When in reality, it's the opposite. The one that took longer to get there is the one that ultimately ends up having more total heat. So the 30-gram one will ultimately have more total heat, okay? It's going to take longer, but the reason it needs to take longer is because it needs to absorb more heat. So even though these are the same substance and they are going to ultimately be at the same temperature, this one will have more total heat in the end because it has more particles that are moving at that speed. Okay, imagine you put a 10-gram sample of iron and a 10-gram sample of water in a 75-degree oven, okay? So we're assuming that these kind of start at room temperature, which is about 20 degrees Celsius, and we have iron and water. And as you know, with your experience, from your experience with metals and water, metals tend to heat up really fast. Water takes a long time to heat up. So which sample do you think will reach 75 degrees first? You probably, if you were guessing, you probably guessed iron, and if you did, you would have guessed correctly. Iron will reach that first. Even though they have the same mass, and they're getting up to the same temperature, the iron's going to get to that temperature first. Iron just doesn't need as much heat in order to reach that temperature. It's just something about the particulate nature of the iron structure. It just doesn't need to absorb as much thermal energy to get up to 75 degrees Celsius. Water is the total opposite of that. Water needs to absorb a lot of energy to get up to that temperature. Water is going to really lag behind, but it'll get there eventually. And once it does, the water is the one that's going to have more total heat. Again, because it took longer to get there, that's kind of our hint that once it's there, it's going to have more total heat in the system. Even though they're both going to be at 75 degrees and they're both 10 grams, the water will actually have more total heat. So it's not just the mass that affects how much heat is something. It's actually the nature of the substance itself also is a determining factor of how much heat is in something. All right, then the last one, imagine you put a 10-gram sample of iron in a 200-degree oven, and you put another 10-gram sample of iron in a 300-degree oven, okay? So same samples, same substance, same size. Which sample will reach the oven temperature first? Obviously, the one in the 200-degree oven will reach it first, just because it doesn't have as high to go. This one will get there eventually, but to get there, it needs to absorb more heat, so it's going to take longer. So once both samples have reached the oven temperature, which one will have more total heat? Obviously, the one in the 300-degree oven. So this is something you probably knew already. You know that something with a higher temperature is going to have more heat. As long as they're the same substance, these are both iron, and the same mass, the one with a higher temperature has more heat. But when they are different masses, that kind of throws a wrench in things. More mass requires more heat to be at a certain temperature. And different substance identities also throws a wrench in the thing. Water is one of those things that has just, if you have a sample of water at 75 degrees that's 10 grams, it just is holding way more heat in it than 10 grams of iron at the same temperature, okay? So the main theme I want you to take from this is there's three things that determine how much heat is in something. It's temperature, obviously, the identity of the substance, and its mass, okay? Its mass probably kind of makes sense. Its temperature kind of makes sense. The identity of the substance is the thing that's the most poorly understood. And we're going to talk about all three of these factors that affect heat, but I'll spend a lot of time on this one. The identity of the substance and how that affects the heat content is called specific heat. Water's specific heat is very high. That means it requires a lot of energy to raise the temperature. Metal's specific heat is very low. It doesn't require much energy at all to raise the temperature. Okay, so with that in mind, we're going to do our notes. You just need a piece of notebook paper and turn it, this time, let's turn it sideways because we're going to make a little chart. So just make 4 columns like that. The first column is going to be the definition. The second column will be a definition. The third column will be the unit, and the fourth column will be the symbol. Okay, so we're going to talk not just about heat and give that definition, but also the factors that affect heat and give those definitions and the units and the symbols that we use. So the first thing I want to talk about is heat. Okay, like I said, heat is not quite exactly the same thing as temperature. I like to think of heat as the total thermal energy in a sample of matter. Okay, the total thermal energy in a sample of matter. So heat and thermal energy mean the same thing. And as we learned in the last objective, thermal energy is a type of kinetic energy. It's the movement of the particles the substance is made up of. And I like this word total. It really gets at the idea that, if you had a pebble and you had a rock sitting out in the sun and they were made of the same substance and they were at the same temperature, this one would end up with more total heat just because it's a bigger substance. So it's the total thermal energy in a sample of matter. So it makes sense that if these were the same substance at the same temperature, this one's going to have more heat in it. The unit for heat is joules. You can write, it's Joules. You probably learned that. That's the unit you used in physical science for any type of energy, not just thermal energy, but any energy. A joule is a pretty small amount of energy. So a lot of times in chemistry, we actually work in kilojoules. Make the K lowercase and the J capitalized. So a kilojoule is 1,000 joules. We tend to use that a lot because a joule is a pretty minuscule amount of energy. When you add a joule to something, it doesn't really change the temperature of it all that much. But adding a kilojoule is a little bit more meaningful. And the symbol we use for heat is a Q, a lowercase q. I know it's kind of weird that they don't use an H for heat. Sorry, let me back up. When I say symbol, it just means like in a formula, this is what we use. Just like when we talked about pressure, the symbol for pressure in a formula was P. Even though the units were like ATM or mmHg, the symbol was P for pressure. So heat symbol is Q. So if you ever see Q in a formula, they mean heat, a lowercase q. People always wonder like what that is. They think it's a G, but that's how I write my lowercase q's. Or I guess some people do it like that. All right. So now let's do the factors that the three, oh, I forgot to write the objective at the top, sorry. This is objective I2. So this is the factors that affect heat. Factors that affect heat content. I like the word content just because it really heat content kind of emphasizes the idea that the heat is this like total amount in something. Total amount of thermal energy in something. So the three factors that affect heat content. The first one, as we saw in the do now, was temperature. Okay, that makes sense. That the higher the temperature something is, the more heat it's going to have. The definition of temperature is quite different from the definition of heat. By definition, temperature is the average kinetic energy of the particles in a sample of matter. So what that means is like, if you have a glass of water that's 20 degrees Celsius, it's at room temperature, all the particles in it are moving, and the 20 degrees Celsius is a representative of their average speed. Some of the particles that are hotter may be moving a little quicker. Some of the particles that are colder may be moving a little slower. They're not all exactly the same speed, but temperature gives us an average read of the speed of all the particles. So notice this word average, okay? It's very different from this idea of total. Go back to the pebble and the rock that are the same temperature sitting out in the sun. Let's say they're both, I don't know, they both heat up to 30 degrees Celsius in the sun. Their particles are moving at the same average speed. They have the same temperature. But this one has more total heat just because it has more total particles moving at that speed. The unit we use for temperature is usually degrees Celsius. Sometimes we use Kelvin as well. The symbol we use for temperature is a capital T. That one makes sense. All right. Second factor that we talked about in the do now is mass. Okay. Mass is a measure of the amount of matter in an object. Which you already knew. The unit we usually use for mass is grams. Sometimes we use kilograms in some of these problems that we're going to do in the next objective. And the symbol for mass is a lowercase m. So when you see a lowercase m in a formula, it's not meters, it means mass. It means this is where you plug in the mass. All right, and then the last one is the most, you've been talking about temperature and mass your whole life in school. The last one you probably have not talked about before. It's something called specific heat. Okay, specific heat is not heat. Specific heat is like a characteristic of something. It's kind of like density. Just like water has a density of 1, water has a specific heat of 4.184. It's a characteristic about a specific material that you look up in a chart, basically. I'm looking in the textbook now for the specific heat chart. So let me see, there it is. So like if you wanted to know the specific heat of something, you would look at like a reference chart like this. And it's right here. This column right here says specific heat. Okay, and you can see it gives the specific heat for all the different elements on the periodic table. You know, there's other charts that give it for compounds. If you become an engineer, you will definitely be looking at up the specific heats of all different types of materials that there are that are used, you know, to build stuff. The definition of specific heat is it's the amount of energy needed to raise 1 gram by 1 degree Celsius, okay? And that varies depending on the substance, okay? Some substances like water, you need to add a lot of energy just to get a gram of water to go up by 1 degree. Substances like metals, you barely need to add any energy to get 1 gram to go up by 1 degree. So that's why if you put a piece of metal in the oven and you put some water in the oven, the metal's going to get to the oven's temperature faster because the metal really just doesn't need that much energy to make the temperature go up, whereas water needs a lot of energy to make the temperature go up. And it has to do with different characteristics in terms of like how packed the particles are or the molecules or whatever. It has to do a lot with the physical nature of the particles that are in the substance. But basically, specific heat is just something you look up on a chart. And it varies greatly depending on the substance. But basically, metals tend to have a very, very low specific heat, okay? I should actually write the word very, that's kind of lazy. Very low specific heat. They heat up really fast and they cool down really fast. So they don't need to absorb much energy for their temperature to jump up. They also don't need to release much energy for their temperature to go down. That's why if a piece of metal is in the freezer or outside in a snowstorm, it gets really cold really fast. It doesn't need much heat to change in order for the temperature to change pretty drastically. That's why we make all of our cookware out of metals. You know, when we put a pan on the stove, we want that pan to heat up so we can cook our food in it. We don't want to be adding tons and tons of heat to the pan with its temperature just like barely creeping up. Things like sand and concrete, they tend to have a somewhat low specific heat, not as low as metals. Like if you were at the beach and you had a piece of metal on the sand sitting out in the sun, the metal would heat up the fastest because it doesn't need much energy to get hot, but the sand would heat up pretty fast as well. Or the concrete sidewalk would heat up pretty fast as well. These don't need a whole lot of energy for their temperature to go up. And if you imagine yourself being at the beach or at the pool with a concrete sidewalk, you know that the part of that area that doesn't get hot is the water, okay? Water has a very high specific heat, one of the highest that there is of any substance. That's why they say like a watched pot never boils, if you've heard that term on the stove, because when you're trying to boil water, it just takes forever, you know. You just need to keep adding heat and adding heat and adding heat and adding heat, and finally the temperature will start to go up. So that's why water at the beach, you know, if it's 11 a.m. at the beach, the sand is really hot, the water's not that hot yet. They both absorb the same amount of energy from the sun, but they are just, water needs a lot more energy to get hot than sand does. So they're absorbing the same amount of heat. They have the same amount of heat. It's just water's temperature is not that high yet. Compared to the other things. And the same thing at night. If you've ever gone swimming in a pool at night or gone swimming in the beach at night, these things cool off really fast and get cool, whereas the water is cooling off. The water just has a lot more heat that it absorbed over the course of the day that it needs to give off. So it takes a lot longer for the water to cool down. All right. So the unit we use for specific heat is it's a compound unit. It's the amount of energy we need to raise 1 gram by 1 degree. So obviously we calculate energy in joules. So it's the joules we need per gram per degrees Celsius. So it's joules per gram degrees Celsius. Technically, these are being multiplied by each other. So sometimes you'll see it written like that. Sometimes you'll see it as a dot. Sometimes you'll see it like this. you know, with the sideways slash and then this in parentheses to show that it's all on the bottom. But again, we read it joules per gram degree Celsius. Don't think that this is like a formula you need to plug stuff into. This is a unit. Okay, this is not a formula. If it was a formula, we would have formula symbols. I'm going to write the word formula. Formula symbols are the symbols we use in a mathematical formula where we plug stuff in. Units are the things that come after the measurement. So this is a unit. So like water specific heat is 4.184 joules per gram degree Celsius. So I'll show you, that's actually on your pink sheet. I think, yeah, it's right here. Yeah, right here. Oh, let me get to this last part. The symbol we use for specific heat is a capital C. That is not Celsius. Celsius was a unit for temperature. Capital C means this is where you plug specific heat into the formula. So on your pink sheet, you can see C, which is specific heat for H2O, is 4.184 joules per gram degree Celsius. Again, this is just the unit. This is not a formula, okay? In the next objective, we're going to learn this formula where we plug in heat. Here we plug in mass, here we plug in specific heat here, and we plug in temperature here. But that'll be in the next objective. Okay, so that is the summary of the 3 different factors that determine the heat content of something. So that's it for objective I2.